1905 and 1915, he knew that he had in his hands a tremendous new tool that would allow him a deeper insight into the universe. And one of the first problems that he turned to, the first application of his new theory of gravity, was cosmology, was to understand the universe. And in 1917, he proposed a cosmological model that I think of as Einstein's cosmos. It had two basic ideas. One is that gravity shapes the universe. The most important force on very large scales that shape the behavior of the universe is gravity. This was thought back in the time of Newton, so he adopted this idea of Newton. But the new ingredient that Einstein brought to this game is the idea that gravity is curved space, that it's related to space. Now, according to the bylaws of in the Union of Public Lecturers, I'm allowed to give one equation. I'll show one equation. You're not responsible for this on the final. And talking about Einstein, surprisingly enough, the equation is not E equals mc squared. That would be too easy. It is the equation that describes his theory of general relativity. And it looks like one equation, because there's only one equal sign there. But actually, it's shorthand notation for 10 equations. There's really 10 equations represented there by that thing that looks like one equation. Now, technically, Jim took general relativity at Chicago. He would say, yes, there's 10 equations, but you only have to obey 6 of them. So it's just like the 10 Commandments, you know? Or are optional. 6 out of 10 is a pretty good day for a lot of people. And these are the 10 Commandments, the origin that we understand on which we base our understanding of the origin of the universe. So let me say a little bit about these equations and describe what these things mean. Kappa is 8 pi times g. G is Newton's gravitational constant, and c is the speed of light. Now, the only crucial thing that I'd like you to understand about this equation is that it has a left-hand side and a right-hand side. That's not so tough. On the left-hand side of the equation is everything that describes space, time, curvature, warping of space and time, and the expansion of space. And on the right-hand side is all of the information about the distribution in the universe of mass, energies, particles, and forces. So Einstein's theory connects the curvature and how space and time behave with how mass and energy and particles and forces are distributed in the universe. So Einstein looked at these equations, and he looked for a solution to these equations that he had developed just a year or so earlier, and he looked for a solution that would describe a universe that is static, that is unchanging, because he thought the universe was static. He did not think that the universe expanded or changed, or there was a beginning of time, a beginning of the universe. He thought that the universe we see today is the universe as it always existed. So he went back and looked at his equations, and he was dismayed to discover that his equations that he spent 8 years developing did not have a solution that described a universe that was static. So he introduced something on the left side of the equation that he called the cosmological term, and he had a cosmological constant denoted by the small Greek letter lambda. Now, In the next 75 years since he did this, we've made great advances in physics. We have moved this term all the way from the left-hand side of the equations to the right-hand side of the equations. It took a lot of work. And we promoted it to a capital lambda, and instead of a cosmological term, we call it dark energy. And I'll come back toward the end of the lecture and talk about why we think that there is dark energy. So Einstein's cosmos involved ideas that gravity shapes the universe, gravity is curved space, that the universe is static, and this required a cosmological constant. So in 1917, this was the standard picture of the universe. Now, I think that only here, at this point, did cosmology actually become a science. Perhaps the hallmark of science is that the theories of the greatest scientists, the ideas of the greatest thinkers, can be falsified. If a theory or an idea cannot be falsified, according to Karl Popper, it ain't science. So now cosmology becomes a science because this cosmological view of Einstein could be shown to be wrong. And in fact, it was shown to be wrong by Edwin Hubble in 1929, when Hubble discovered that the universe expands, and a consequence of his discovery that the universe is expanding is that the universe began some finite number of years ago with a bang. So our modern view of the universe is the Big Bang. And I can just summarize it, the idea that our universe emerged from a state of high temperature and density 13.8 billion years ago last Tuesday. And today, for the last 13.8 billion years, has been expanding and cooling. The universe is dynamic and evolving. Now, when I say that the universe evolves with time, how can I prove that the universe evolves with time? Well, cosmologists and astronomers are lucky because we have time machines. We can use time machines to see the past. The time machines we use are telescopes. And here are some examples. The Giant Magellan Telescope in Chile that we're involved with. The South Pole Telescope that we manage at the South Pole. The Hubble Space Telescope, named after Edwin Hubble. And I will argue that the Large Hadron Collider in Switzerland is a telescope. The telescopes are time machines because as we look out in space, we look back in time, because it takes light time to reach us from the objects we observe. The farther away you look, the further back in time you can see. So that's why the people in the back of the room seem a little bit younger to me than the people right here in the front row. If you want to look young, don't stand very close to a person. You look older. For every foot away you get from a person, you appear a nanosecond younger. The farther out you look, the further back in time you can see. So as we use telescopes to look out in space back in time, we can actually watch the universe evolve. Now, as we watch the universe evolve, one of the things that we try to understand is how the composition of the universe changes. What is the universe made of? A simple question. Well, I'd like to talk now about the present composition of the universe, and that's illustrated in this slide. as we look out in the universe today, there's about 0.005% of the universe in the form of radiation, and most of that radiation is not in the visible part of the electromagnetic spectrum, but in the microwave region of the electromagnetic spectrum. This slide illustrates why chemistry is not important. I don't know why we make students study chemistry. Chemistry, the chemical elements only amount to 0.025% of the total mass and energy of the universe. And to me, it seemed like a waste of time. Elementary particles known as neutrinos make up about a larger fraction than the chemical elements. Stars that astronomers look at, a little bit less than 1%. Most of the normal stuff in the universe is a hot gas of hydrogen and helium that makes up about 4% of the mass and energy in the universe. But if you add up everything that we observe and can account for and understand, it only amounts to 5% of what's in the universe. 95% of the universe seems to be invisible to us. 25% of the present universe is in the form of dark matter, and 70% of the present universe is in the form of dark energy. And that's the title of the lecture today, Mysteries of the Dark Universe. It's dark matter and dark energy. They seem to be different. Dark matter pulls things together, like you would expect gravity to behave. Dark energy seems to push things apart.